Right, so let's talk about SQL. So as you might already know, SQL, or Structured Query Language, is the, it has been the standard way we have been interacting with relational databases for quite a while, and probably will still be with us for quite a while more. But the intent was to be able to implement these ideas, that to have a formal representation implemented in such a way that were perhaps a little easier for folks to start using it. And the idea was to write it and make it somewhat of a English-like pseudo conversational interaction between an operator and a data set. So the most basic type of operations are the select operations, where you specify which fields you want to retrieve from a particular table without any predicate. And so this would return all the records from that table with all the fields that are listed. And we say that the select part is the select clause, and the from part is the from clause, right? And we can distinctly talk about one or the other individually. As mentioned earlier, the select allows us to filter the entire data set vertically, right? Where we might have millions of records, but we only might really care about only a subset of them. So select allows us to filter vertically on which rows do we want, and then projection allows us to filter which fields do we want in those rows. We'll be using the same 6 tables that represent our small university database, and querying things about that database. So here's a very simple query that is retrieving the student name and the graduation year from the student table. Things to note here is that the fields are prefixed with the name of the table. It's an optional syntax. It's only needed when there's an ambiguity of which field exists inside of which table. In this particular case, it's only one table, so there's no ambiguity that the student name and the graduation year are from that particular table. Right? So typically, we would not use the prefix in front of the field. We can use aliases to rename the tables, right, and give them perhaps a more meaningful or less meaningful or more abbreviated version of the name of that table, which we can then use as the prefix later on in our queries. Later on, we will find this very useful when we want to be able to join one table with itself. Right? You might have records in one table that refer to other records in the same table. Right? Maybe you have managers, right? You have employees where some work for other folks. Right? You might have managers that manage other employees, right? And they might have other folks that report to them. So you have this kind of hierarchical representation. So you have so you might have, in the employee table, you might have foreign keys that refer to primary keys of the same table. So to join them, you need to be able to rename these tables and give them aliases so you can join them together. So we'll take a look at that a little later with self-joins. There's some shorthands. If you want all the fields, right, you don't have to just list all of them. You can just use a shorthand, just star. Right, allows you to retrieve all the fields for that particular table. Or you can prefix it with an alias or the name of the table as well. Okay. Here we have a join that we haven't introduced just yet, where we are retrieving data from 2 tables, right? The department and the employee table. We're listing all the 2 tables that we are joining, and we're joining it by providing here a predicate that says that we only want those records where the foreign key and the primary key are the same with one another. But in this case, the thing to point out here is that these fields, where name and dname, actually belong to 2 different tables, right? Where this might be the name of the department, and this might be the department name of an employee, right? Actually, we don't really know which one belongs to which one. If we need to know, perhaps we would have to prefix it, yes? But in this particular case, if there's no ambiguity that the department name is called department name and the employee, and that name is the name for the department, there's no ambiguity that you don't need to put the prefix. If there would have been an ambiguity, where this would have been called also DName for the department name, and DName for the department name and the employee, and then there's an ambiguity. Which field do you mean, right? For which table? So you would be forced to provide the prefix in front of the field. Okay. Here's a very simple example of retrieving all the persons from the table persons, returns the entire table, or only a subset of the fields. Right. Here's a projection, right, of retrieving all the persons. So we have last name and first name only. Distinct. Here we have a query where we are retrieving only the city field of the persons table, and we might have, since it's not a primary key, you might have repetitions in there, right? You might have fields that are repeated. In this case, we might additionally ask that we want distinct values only, right? So that if we find repetitions in the fields, we want them filtered out. Right? Every time you ask more from the database, you are incurring in time consumption, right? You're paying for performance, right? If you're asking for distinct, notice that you're asking the database to keep track of things to see if they repeat. Right? For instance, if you're looking at Dracut here, somewhere you need to keep track that I just saw Dracut, and every time you look at another one, you have to go in through that list to see if that one is in the list. Right? If it's not in the list, then it's okay. If it is in the list, then I'm going to skip over it. Right? But every time we ask for things like this, we need to consider. Say, well, distinct, that means that we need to keep track of additional lists, and that's going to occur in a linear search, right? And so this is doing a distinct on this, it's much more expensive, right, than just not doing a distinct. So all these kinds of things you need to consider, when you are optimizing and considering improving performance. Data types, of course, when you declare the fields are of a particular data type. They're either numeric, integer, float, date, right, or character, strings. Now the SQL provides multiple operations, mathematical operation or string concatenation, string operations or date operations that you can operate on the fields that are being retrieved from the database, right? Or that you can also cast from one data type to the next data type. So, for instance, operations on strings. All the operations that you could think of in a programming language are available. Things such as lower strings, upper strings, lower. You can trim it. You can find things. You can do substring. You can do concatenation. All the operations that you would think of in a programming language are here. You can calculate the number of characters in a string. You can calculate substrings. You can retrieve the current user. So if I log in, I am logically represented by this global variable that I can then use as part of my queries. Perhaps I want to retrieve only the records that belong to me, right? Only the sections that I'm teaching, right? Only the courses that I have authored, right? And if I query, I get a different response if somebody else queries it, right? Because they log in as someone else. It's the same query. Concatenation, you can allows you to pattern match fields against a particular pattern, right, and retrieve whether it's true, whether a particular string matches a particular pattern. Very, very powerful, very expensive too. So here an example of Einstein mapping or matching with _i %i underscore, where underscore matches a particular any character, percent matches any number of characters, right? And so here we're saying any letter followed by I, followed by any number of letters, followed by I. So the second I and the second to last I, right? Something that matches like that. So certainly Einstein matches that. Like also has wildcards that allow you to match, the beginning of a string, the end of the end of a string, things like that. And here's an example of using it right at the end, right at the a where clause. Again, we haven't seen where clauses, but it's where you establish the predicate, a particular field, and then pattern matched against some other one. Here's a couple of other examples, right, of retrieving only those persons that live in a city that starts with LO. Notice that it's case insensitive. That's by default, SQL is case insensitive. You can turn on case sensitivity as well, but typically is only case insensitive by default. There's some date operations that you can calculate, retrieve the current date, and then retrieve, ask for different portions of that date, such as what the year is, the month, the day. You can do also interval calculations. You can add so many months, you can subtract so many days, and you can do date operations, date arithmetic, right, to calculate all sorts of really cool date computations. Current date gives you the current date as by the clock of your machine, and then extract allows you to retrieve different portions of a date. Date typically has this format, although this format might be different for different vendors, but this is the most common one, right? Whereas is 4-digit year dash 2-digit month dash 2-digit day. So that's the most common one, represented as a string, right? And then you can ask it to operate, to cast it as a date, parse it as a date, create a date object, and then operate on it to retrieve the month, the day, or the year, and then use it in interval operations where you can add 7 months, subtract 3 days, right, and then retrieve a resulting date, right? Plus, there's a whole bunch of other operators, other formats, depending on what your vendor is. So you should always check, what your particular vendor, the way they particularly represent dates is not completely standard. Most folks, most database support the basic representation of year, month, day, but different vendors might have other names for different for different data types and different representations. Like SQL Server, you have date time, small date, timestamp. Most everybody supports timestamp, right? And most everybody supports date time. Also, there's a plethora of operators that allow you to do all sorts of arithmetic operations on dates. And again, these are also vendor specific. So here's some in MySQL that allows you to do date addition, subtraction, retrieval of a particular part of a date, or formatted in military or European or some other locale, represented in different formats. SQL Server has its own types of date operators. Here's a couple examples on SQL Server being able to convert dates into various into different formats, and they have documented all the different formats have a different number. So converted into one, it's converts it into a small year. So this is 07, 101. It's 2007. And using the European notation, right? You have day, month, and year, I believe. All right, so let's go back to the select statement, and perhaps use some of these operators. Here we have a select from the students table that we've renamed to be S. We're retrieving all the fields for the student table. And then we are doing an extend, right? We're doing an extend where we are on the fly calculating the graduation class, right? We are subtracting the graduation year minus 1863, and we are renaming that field, this brand new field, a graduation class. So this is not a class. This is not a field that actually exists. So any field that can be calculated on the fly should not have been stored in the database in the first place, right? Anything that can be calculated, you don't want stored in the database. Here we are using a constant BC and adding it as a new field, right? So that we can generate a brand new data set of new students, perhaps, or I'm sorry, of students that have graduated from BC. So here's the output of where the last two fields have been dynamically calculated. One of them is presumably the subtraction of the graduation year minus the foundation year, and the other one is just constant BC. So here's a running example of calculating the new ID for a graduation decade of each student. So given the students that we have, we want to create a new data set of of students where we're going to dynamically come up with a new student ID with graduation year as the graduation decade. So let's add to this. Here we have renamed the SID. We've renamed it as new SID, and we are renaming the graduation year as graduation decade. And then we're going to add a couple of things. We're going to calculate the new SID. We're just going to do a string concatenation of the student number with the original student ID. So the new value is going to be student number with SID. And the graduation decade, we're going to do a computation of the graduation year divided by 10. So we're going to lose the last digit. So it's kind of rounding, right? We're first dividing it and then we're multiplying it again. And so we're dropping the last digit, and so we can find out what decade did you graduate, right? In the 1980s, 1990s, 2000s, 2010s, which decade did you graduate? So we're rounding up to a whole decade. So you come up with things like this, right? Student 1, 2, 3 all the way, and then student names and the graduation decade. You can also intermix inside of your queries. You can intermix conditionals, such as case and ifs, if then else, as part of the query. And so here's a very simple, trivial example where, as part of a query, given a simple table 1, 2, 3, we can take a look at the condition of what the current value is, 1, 2, or 3, and depending on as we compare it. Compare the value of a particular field across multiple possible options, we then provide a particular result for that particular option. So let's look at an example where we're selecting from A, from the test table on the right-hand side, and we are retrieving the original value of A, right? We're retrieving just unchanged, but here we are generating a brand new field, whose value is going to depend on the value of A, right? So we're saying, if it's 1, then the value is going to be 1, right? If it's 2, then the value is 2, or then if it's anything other than 2, it's just going to return other, right? And that's where 1, 2, and other come out. Notice that the case, the name of the field, has been dynamically chosen by the database, since we didn't give it any particular name, right? Typically, we would want to provide an as here, where we give it an actual name, right, of the name of the field. If we don't provide a name of the field, the database will choose it for us, right? For instance, it'll grab the name of the function that was used to calculate this, right? And we'll come up with some name. If you have many cases, it'll come up with case 1, case 2, case 3, and it'll just randomly choose a particular name for you. Typically, you want to choose a name, specific name, deliberately, as opposed to having the database choose it for you. So there's a couple of different syntax for accomplishing the same thing, where you have the same. Notice that here. The when, it's fairly powerful because each one has its own predicate, right, independently from another predicate. Right? You can have here something comparing A with something, B with something else. Right? You can have a fairly complex predicate, each one. Right? Whereas you have a simpler predicate, a simple version of this, where you have a given expression, a single expression that then gets compared to multiple values here. This is the more classical example of the switch case in many languages, where you're giving a single expression, and that expression gets evaluated and then compared to multiple different values. So this is more like that. You have one single expression and then gets compared to multiple values. But this one's so much more powerful. This is almost like just having multiple if else, if else, if else, if else, if else. So this one just compares A against 1, 2, 3, and so forth. So this is the equivalent of what we had earlier. Or you can have let's use the case here. Here we're taking a look at we're extracting the year, right, and we're subtracting it from the graduation year, right? So that we can determine whether this is an alumni, right? So that if it's a positive number, then you're an alumni. If you're not, if this is negative, then that means you haven't graduated yet, right? So let's see. So if a current date is 2011, then the extract date is 2011, and if the graduation year is 2007, then 2011 minus 2007 gives you 4, right? So extracting all that and subtracting that gives you 4, right? So this retrieves how where are you in your graduation? If your graduation year is in the future, if this were 2012, 2013, then this would give you a negative number, right? So you're not yet an alumni, right? So if it's positive, that means you've graduated. If it's negative, then you have not graduated yet. So given that query of Q69 that calculates all the how many years is left for graduation, we can generate another query where we can check to see if that years that to go, if it's positive, then we can calculate. We can come out and say that you're an alum, right? You're alumni, right? You have graduated. Otherwise, and then you're still in school, or you haven't graduated yet. So here's an example of using a view later on to calculate other things. So here's an example of using the case, right? Where we're evaluating an expression, and depending on that expression, we give a result. It's less verbose, a more compact syntax is to just use an if statement. We have an if, you have the predicate, and then the outcomes, right? The true and the false outcomes of the if statement. Whether if it's true, it returns alum. If it's false, it returns in school, and then a particular name, renaming that particular field. All right. So this is certainly, if you just have one single predicate, then this is certainly more convenient. But if you have multiple, the case is more convenient. Let's look at the from. Let's focus a little bit on the from clause. We've talked a little bit. So we have the from where you can provide any number of tables, and you have optional aliases, right? That can then be used as part of the select statements. And again, you would use them if you need to disambiguate between different tables that might have the same name. For instance, here we have a self-join, right? You have 2 students that I'm not sure how they would be related to each other, but anyway, so we have student and student 2. We have two student tables. So to be able to distinguish between the 2 student tables, we've given them different aliases, right? In a more realistic example might be an employee table, right, where you have employees that report to other employees. So where you might have a foreign key of an employee that says who you report to, right? So you point to some other employee, right? So if you wanna find out who reports to someone, then you need to join them. You need to join. Well, find me all the employees that report to a particular person, right? So you can join them like that. So you had employee E1 and E2, where, right, the reports to is equal to the primary key of some other employee. Make sense, right? In that case, you do need, that's a self-join, right? In that case you have to rename the tables, right, and use the aliases to join the primary keys and foreign keys of the same table, right? Combining tables. So to combine tables, we use the join syntax, where we list the names of the 2 tables that are being joined, right? We have the table 1 and table 2 are being joined on a particular predicate. So this is the predicate on which we are identifying the primary keys and foreign keys that relates the various records. Now, there's several different versions of the join table. We can have left joins, right joins, and full joins. That allows us to, and the inner join. The inner join is the more common one, right? It's the one that we typically understand, and it's the most logical, right? Where you have, fields of one table are somehow related to fields in some other table, right? Where you have foreign keys of one table referring to primary keys in some other table, and obviously those records are meant to be related to one another, right? So those are referred to as the inner joins. Okay? It's where you might have two sets and the two sets overlap, right? So we want the ones that overlap. We don't want the ones that don't overlap at all, right? So that's why it's called inner join. But sometimes you might want also the ones that don't match, right? You want the ones that match plus the ones that don't match for a particular set. So to illustrate these examples, let's consider these two tables. We have Boob, Dole, and Garcia, and we have an orders, right? So notice that here's a purchase order, or person's order, sorry, person's ID, person Boone, Dole, and Garcia, P1, 2, and 3. And here are the orders that have been ordered by Garcia. These two were ordered by Boone, and no one ordered this product over here. There's an order there that's orphaned, right? It's an order that it's orphaned, right? Nobody has reference to it, right? So anyway, so let's see. Let's take a look at it. If we join these two, and we say the persons and the orders, and we join them on the person ID on both tables, we come up with the results, right? We have Dan and Charlie, plus is an order that doesn't match anybody, right? So that one, notice that it's not listed here. It makes sense, right? That order it's orphaned, right? Nobody is not matched with anyone else. But sometimes we might want to retrieve those records, even the ones that don't match, right? So for that case, we have the left join and the right join. The left join allows us to do those things, right? Meaning we want the inner join, plus we might want the records that don't match. And we have to specify, well, which ones? The ones from the left table or the ones from the right table? Notice that we have a left table joined with a right table, right? So left join says, I want the ones that match. I want the inner join of both of them where they match, plus I want the records from the left that don't match. Okay, why would you ever want to do that? Nevertheless, you can do that, right? You can do a left join, or sometimes referred to as a left outer join. So notice, let's go back to the original example where you had the people and the orders. And when you left join, you basically are doing the inner join. Here it is, right? The first inner join that we looked at earlier, plus this Bob Dole who didn't order anything, right? So it has no matching record in the orders table, right? And here it is, right? It's returned to us as a person because we asked for even the ones that didn't match from the person table, even though we didn't match it. So obviously it's going to be a null on the ones that it's padded with nulls on the field that didn't match. Or we can ask for the right join as well. We can ask for the right-hand side or the left-hand side. So here's an example where it might make sense, right? So sometimes it makes no sense. Why would you normally we think of only wanting the records that match. Why would you ever want the records that don't match, right? Well, in some cases you do. Here's an example where the question is as follows. It says, find the name of each staff member and his or her spouse, right? If the question ended there, that says, find the name of each staff member and his and her spouse. If the question ended there, that's just plainly an inner join, right? Because I want the staff, I want every staff member, and by the way, I want their spouse, okay? But if you add an additional qualifier that says, if any, that means that person might not be married. Okay, so there might be no record for the other spouse. Right? So what do? I don't want the staff if they're not married. Right? I'm not going to invite them at the Christmas dinner because they're not married. So no, I do want the list of them as well. Right? If they're married, I want their spouse information. If they're not married, I still want their staff member, even though they don't have any spouse. Make sense? So subtle things like that, right, of questions in certain queries, right, might make the distinction on whether using an inner join or left join or right join. Make sense? So in this case, we do want a right join or a left join because we want the records even though they might not have a reference to the other tables, right? So if you have these two tables where you have a staff and a spouse, right, where the staff has a primary key of the social security number, and you have a spouse that also has a social security number, but it has a primary key, being a foreign key, ESSN, that reference the primary key of the staff, there might be no record because the person might not be married. Okay, so we would do something like this. Retrieve for me the staff first name and staff last name, also the spouse first name and last name, if any. They might not be married, so these might be null, and it's okay. I still want them, right? Because otherwise, it won't even return to me the staff information, right? So in this case, we do if we do an inner join, we are left with only the staff members that are actually married, right? And we would be left out of the ones that are not married. But the if any gives us the clue that it has to be a left join, right, or a right join, right? If we turn this around, it would be a right join. So here we have the staff. We also want the staff that are not married. So that's a left join. Make sense? A right join is just reversing the order in which we are operating. We want the records from the right-hand side table, even if they have no matching. Right. So in this case, if we have the original orders table, we know that there's a couple orders that have no match with the person table. But we want the orders anyway, right? So we're saying right join order, meaning we want the orders, even the ones that don't match. So here's all the orders, and some of them have no matching record with the person. So those are padded with null. And then we have a full join, where we want to return all the records, even the ones that don't match, right, on both cases, right? So we would do first the inner join, right, and then list all the records that did not match, padded with the records with the fields with nulls of those records that didn't match, right? So we have Bob Dole here with no matching order, and then we have an order here that has no matching with the person, right? Okay. If you want to specify multiple joins, typically you can combine them using parentheses, right? In groups of two, right? Where we can have a join of two tables, and the output of that can then be joined again with some other table on some other predicate. Each one would have its own set of tables that is being joined with its own predicate, which can then be fed into the next join with another table with its own set of predicates, right? And now this could get fairly hard to read, right? Especially if you have 2, 3, 4 joins. Obviously, the more things that you're joining, the more expensive your query will be, right? Searching on a single table, it's linear. Searching on 2 tables, quadratic. Searching on 3 tables, cubic, right? So it becomes exponentially hard to join many tables, right? Oftentimes we try to look at ways that we can improve performance, such as maybe creating a view, or maybe a denormalized, materialized view, or some indices. We'll talk about that a little later. So here's an example on a multiple join, on a single join that we're joining 2 tables, and here's an equivalent implementation of the same exact join, but using a different syntax, right? Instead of using the join syntax, right, and then providing the predicate using the on keyword, instead we are using the plain old where clause, which we haven't talked about yet, right? The where clause is where you can specify predicates, right? You can say, where the following 2 fields match. Now the where clause allows you to specify any predicate, right? Here specifically, our particular predicate is equating 2 fields that are related to one another, primary key and foreign key. Yes. So here is just a different way of writing a join, right, where the predicate is two joining fields, right? Now we refer to these as two different notations. We call this syntax the explicit join notation, right? We were explicitly telling you that this is a join, right? Whereas when we use the where clause instead of to do the join, what we call that an implicit notation, right? We're not explicitly telling you it's a join, but it's obviously a join, right? We are equating two fields that are related to one another, right? Now let's look at now that's a good segue into the where clause. So the where clause, as we just saw, provides a means for providing the a predicate, right? A predicate, a Boolean expression that has to be true, for all the records that are being considered, and only those records that match the predicate are going to be returned. Now some of these predicates, some of them will be joins, and some of them don't have to be joins, right? They can just calculate whether something is greater than that, or it's within a particular range, or it's spelled in a particular way, right? Or it's in a particular set of valid values. But some of them will be joins, right? If you have more than one table, right? So some of them will be joins, some of them won't have to be joins. So you can mix and match predicates that are joining and some predicates that are just operating on arithmetical values, on whether they're between a particular range, whether they're spelled in a particular way, whether they're in a particular specified set of values, or all sorts of arithmetic operators on whether they're greater than, less than, or not equal to each other, right? Combined with complex ands and ors to create fairly complex Boolean expressions. So here's a couple of really simple examples, retrieving all the persons from the person table who live in Lowell. So out of these three records, we only have these two. And here's a simple example of combining two predicates using the and. We're retrieving only the ones who has a particular first name and a particular last name, and combined with an or that has Bob or Dan, so retrieves two fields, two records, right, with either Dan or Bob. And you can make these fairly complex with using parentheses to establish sophisticated Boolean expressions of the predicate that you're looking for, a particular record that meets that criteria. Now some of these as mentioned earlier, the where clause, you could have fairly complex Boolean expressions of just fields that have value. These are value fields. These are not relational fields, right? These are just fields that keep track of a particular value for a particular field. But you can combine them with joins, right? Where that join different records from different fields. So here's an example of having a join here, actually a double join of students and enrollments, and then also joined again with the section, right? Where here's the implicit version of that, right? Where you have the student ID matched with the enrollments, and then the enrollments matched with the section, right? And if they're both true, then we want that record, right? So this is much easier to read, right? This has become much more popular to write it this way, rather than to write it this other way, right? So folks tend to write it using this syntax instead of using the implicit syntax instead of the explicit syntax. Okay, but they can be mixed and match, where you can have a mixture of join fields, right, plus a mixture of just value fields, right, that you're searching for folks that have a particular name, that are looking for a particular year and whatnot, that you can operate on any of the tables that are listed in the from table, in the from clause. Okay. Between allows you to retrieve values that are or records for fields that are in a particular range, right? You can, and these could be ranges of dates, ranges of strings, or ranges in between two particular values, any values. So for instance here, retrieve all the records that are between Boone and Garcia, meaning that this is going to be lexicographically or alphabetically compare the last name between two ranges. Okay. Or you can also combine it also with not, right? So you can retrieve the fields that don't match. All right, I'm going to leave it here, and we'll come back